Welcome to today's edition of ENGR 315A Online Edition, where we move from bending stress to our next item of interest. So we've said before, shear stress. We said once upon a time that normal stress isn't really uniformly distributed, depending on how it's applied. Well, now we get to talk about how I've been lying to you about shear stress for the past 3 months. Um, it's not uniformly distributed. There's some other distribution for it, and today we're going to mess with it. But the thing I wanted to look at first is if you look at the I-beam in the image there, so that's a steel reinforced concrete I-beam there. But look at how it's broke. Look at how it's broken. It's all the cracks are propagating through the web, and they're propagating lengthwise through the web. They're all almost horizontal, which is wonky. Like if something broke in bending, we wouldn't, which call thinking of like where the stress is highest, we would expect it to break on the flange, on the top and the bottom, right? It's like, what the crap is this? And it's breaking in the middle, and then it's breaking in kind of a way where you have two planes and they slip away from each other and they form this crack. And like, what in the world's going on? You might say, what the crack is going on, but let's look at this. So let's see how far we can go here before I switch over to OneNote. So let's do this. So we're going to look at a example of bending, of an article in bending. We're going to look at 3-point bending and see if we can pull out some issues, dare I say. So I think it's in this one. You guys seeing this presentation?
Yeah, I see it.
Great. Okay. So if we start off with our usual 3-point bending gig, it looks something like this, right? So we got two supports. We got the load in the middle. We know from before, we know from having done this problem already, that let's see if we can do this. Oh, nope, it won't let me. The two support forces, P support, those are equal to half of the load. We know that the shear force is a constant across the two sections of the beam. On the left here, it's a constant. On the right here, it's a negative constant. And we know that bending stress is triangularly distributed through this beam, and it's at a maximum in the center. We have that shear and bending moment diagram already done. It's written out, whatever. So if I go and I take a section of the left-hand side and do my usual whole gig with it, let's call it that. That's something that we can do. It's pretty straightforward. However, what we're going to take one step further is we're going to look at a stress cube in this beam, and look at what the shear forces are on that stress cube. All right, and we're going to see how they're distributed across a face of the item that we're interested in. And before I get too far and give it all away, let's move over and solve this puppy and solve this puppy. So, so here's my guy. Here's my section here. This drawing comes from my beam which is in 3-point bending. So load in the center, supports on the outside. You know that is true. And then I'm going to take a section, say right here. I'm going to get this. Note that this is like a I'm slipping. This is what happens when you have your elbow on a stack of books. And they're all paper, and they're all paper, and they're all paperback. This guy on the one side. This is your front view. This guy over here. This is like a right side view. All right. So come on, let me hear. So this guy over here on the right, sorry, on the left, the one that I'm doodling on, that is looking straight at the 3-point bending diagram that I drew. And then if I go and I look at that section from the side, like I look straight down the length of the beam at what I've cut, that's what this guy is. We all clear on that? Yes, no, maybe? Cool, thanks, Jake. All right, so I'm gonna drop that over there so I can still see answers and stuff. All right, so if I pick a stress cube about now, select this guy up here. If I pick out a stress cube and I look at the forces acting on that stress cube, I'm going to obviously have some bending stress, right? Because we know that in 3-point bending, I have a bending moment distribution that looks like that, where that's the center of the beam. Wow, my handwriting's terrible today. Just as a note, I'm in the process of getting a document camera. Hopefully, to be here by Thursday. So next week, my handwriting hopefully will improve by a heck of a lot. So we know that there's some bending moment just distributed throughout the beam. Because there's a bending moment, we know there's a bending stress because, well, where's my thing? Because which called whole normal stress is proportional to bending moment. We know that. So therefore, we have some amount of normal stress because we are in bending. We know all that is true. And we can even compute all of it for a beam that's in 3-point bending, and you have computed it. That's what sigma A and sigma B are. So if I have my little stress cube here, the stress cube has some area. So force is just a stress times area, right? So that normal stress is exerting a force on each side of the stress cube. Now, are sigma A and sigma B the same, or are they different?
Aren't they the same?
Why?
Because load factors.
What do you mean by load factors?
Oh wait.
Wouldn't it be different because they're different parts of the load?
The different parts of the load. What is that? What does that mean?
Well, one looks like it's on the one's like on the bottom part of like a triangle. Like you see how it's like made like a little triangle there.
Okay. Well, hang on. Let's just look at sigma B now. Why is sigma B distributed like a triangle?
I don't know. That's a good question, Marcus.
What's the expression for bending stress again?
It's mb times y over the second moment area.
Awesome. So at one point, bending moment is going to be constant, right? Constant at a point. I is going to be constant, right? So, but if I, there's my y coordinate. But as I move up and down a cross section, that's just like y coordinate here. Bending, which called the stress caused by my bending moment is going to change, right? So at my neutral axis, my bending stress will be what?
0.
0, right? Because at the neutral axis is where y is 0. At the top of the beam, it'll reach a maximum. At the bottom of the beam, it'll reach a negative maximum. So just by the fact that it's bending stress, we should anticipate that it will be triangularly distributed. Does that make sense, Nick?
Yeah.
Okay.
So is it like all bending stress is triangularly distributed?
It's called every last one.
All right. I think I remember that. Yeah.
Good. The homework will be a little bit easier then.
Oh boy.
You'll be good. You'll be good. Cool. Okay, so we know this case. So the triangular distributions make sense, but are sigma A and sigma B going to be equal to one another?
No, because if it's triangularly distributed, then it's different.
Well, they could be the same triangular distribution.
Well, then it is the same. Okay.
Well, I said it could be. Why is or why isn't it? Just because it's triangularly distributed doesn't mean that they're going to be different. And it
equal and opposite.
Say again?
Equal and opposite.
Okay. Why are they equal and opposite?
Because they're the same. Like at each point, it's the same y away from the center.
Okay, so they're at the same. So they're the same distance from the neutral axis. There's the same second moment of area. Do they have the same bending moment?
One is positive, one is negative.
Well, just because they're on opposite sides of that stress cube. Is that what you're saying?
Yes.
Okay. That's fair, and you're not wrong. But something that we need to keep in mind is this is a stress cube, right? Does it have width?
No.
Why not?
Is the width like large enough for it to really affect the magnitude of the bending moment?
If it has width, it's large enough to affect the magnitude of the bending moment. If it's a differential width, even it'll affect the bending moment in a differential way. And that's the trick. We know that bending moment is distributed, right? And in this case, especially, it's always different at every point. I'm just marking the center line. So if I'm here, say, and I move a differential amount over to the left, some amount dx, say, my bending moment is also going to change by some amount, some small amount, but some amount nonetheless. Meaning that for this in this case, and for most cases really, those two bending stresses are not balanced. The forces created by those bending stresses are not balanced, which is going to create a shear stress. Rather, it's going to require a shear force in order to balance, and that shear force creates a shear stress. That's what this delta H guy is down at the bottom here. It's some horizontal force that is going to be required in order to balance the normal forces created by those unequal normal stresses in order to put that stress cube into static equilibrium. We all on board with that? Yes, maybe.
Yeah, I think so.
Okay.
On board.
Sweet. All right. So.
Going overboard.
So let's get ourselves a little bit more room here. So one thing to keep in mind is that shear force delta H. If I look at my stress cube again, and I throw my shear stresses on it. Whoops, that one's supposed to be going the other way. Okay, there are all my shear stresses. Are they all the same or are they all different?
Wait, what? What would you say, Brother Morris? I'm sorry.
So I got my shear cube. So I got my stress cube here, right?
Yeah.
And I got a whole bunch of shear stresses drawn. Are they all the same? Or are they all different?
Probably the same.
Why?
Because it's a cube. I don't know. Maybe.
Okay. So, I mean, it is a cube, but that isn't why they're all different or all the same. I could have a triangle or a pentagon or decagon, and the answer would still be the same. This cube, it has to be in static equilibrium. That's kind of the condition that we've set here. Everything has to be in static equilibrium. It cannot translate and it cannot rotate. Okay. So as a result, if I have one force here, in order to stop it from translating to the right, what has to be true about the force that's going to the left?
Equal.
Right. Now, if both of those are of the magnitude, this thing's going to spin. So we need to have an equal and opposite moment, but to balance it out. Therefore, all these shear stresses have to be the same, and the shear forces that they create also have to be the same. And we choose a cube to represent it because it's convenient geometrically, because we can say directly that the shear forces are all the same. So as a result, this delta H guy, it's not just the force on one face, because all the shear forces have to be the same, because all the shear stresses have to be the same. It's actually it's called it actually can be equated to our shear force. All right. So, game on. So the good news is that if we can draw a shear and bending moment diagram, we should be able to find out what delta H is. And if we can find out what delta H is, we can figure out what our shear stress is. So I'm not really going to go over the shear bending moments inside of things because I feel like we're all experts on that. And let's skip right into finding shear stress. So if this is our free body diagram for our stress cube, this little guy here, little called tiger striped guy. Let's do a summation of forces on that in the horizontal direction. We'll say that that way is the not x. That way is the positive direction. So on one side, delta H plus the integral of normal stress times dA. dA being a differential area, and I integrate. Sorry, I multiply that with my normal stress distribution to get the differential force on each differential area, and I add all those up. And that's from sigma A, so that's going to the right. Then I subtract contributions from sigma B, which are going in the opposite direction. All that is zero because it's in static equilibrium. We happy with that?
Yeah, I believe so.
What's up?
Those are the sigma A times. That's oh geez, what's that letter called again?
Sigma?
Yeah, well, sigma A times. It's not a sigma A again, but it's a
no, it's a delta.
delta. That's right.
It's whatever you're integrating with respect to. Usually, it's like a dA. If you want to be more precise about it, it's a delta because it means it's a partial derivative, or you're integrating with respect to a single thing instead of a function of something. I think that's the okay way of saying it. So it means the same thing though.
Yeah.
Oh yeah, it's snowing out. Okay, so we got this guy up here. I mean that's our summation of forces. We know that bending stress we can express as the bending moment times vertical times perpendicular distance from the neutral axis divided by second moment of area. So I can substitute in from this. Just going to get myself a little bit more room here. There we go. And say 0 equals, let's be a little closer. 0 equals delta H plus integral M A y over I dA minus integral MB. That's moment at B y over I dA. All right. So I got some more integrals here. Is there anything constant in these integrals that I can pull out? Don't everyone speak at once now.
Oh.
Sorry.
No, you can't. The Y's and the I's.
The I is the only constant, right?
The eyes are definitely constant. Yep.
Wasn't the Y or no? Is that what the MB? I guess you can't because it's being multiplied. Never. Well, you could, but
Yeah. So
Bending moment.
it's called the bending moment at each point is constant. So I can take an MA out and I can take an MB out.
oh,
Because at each point they are constant. However, because there's called if I go back up here, I'm integrating across. I'm integrating across. That was a terrible color choice. Across this cross section, right? Therefore, I'm moving vertically on it. I'm moving in Y in order to perform my integration. Therefore, Y is not constant. Y is varying. So I can pull out the bending moment. I can pull out the I. I can't pull out the Y. So can do this. And I get that. Cool. So if I wanted to group this a little bit, because we all know that factoring makes life fun. Get something like delta H plus MA minus MB of I times integral YDA. What's this YDA thing? What does that look like that we've seen before?
that's just a regular integral, I would say.
Okay, great. But like, what's this YDA? Is that term similar to something else that we've seen?
I have no clue. YDA. YDA. Can you
What
give us?
what was Y squared dA? We touched on it when we talked about bending moments. Sorry, bending stresses.
Yeah, I don't know. I'm not sure what it would be.
Well, Y squared dA is your second moment of area. It's called the integral Y squared dA is your second moment of area. So that means that your integral Y dA, that's your first moment of area.
Oh,
That really helps you. But it's but this is something that, like your second moment of area, we can kind of deduce a way to figure out. It's not as weird and scary as it looks like. And actually, you all have already used this. You all have actually already computed it several times in statics. So hopefully this will be a nice little review for you. So say that I have a box. And I'm looking at some region up here on the box. The first moment of area, okay, and let's establish, sorry, that this line Z is Y equals 0. So the first moment of area for the region that I've shaded here, so this space, if I wanted to compute the first moment of area for that, I'd have to know the area of it. I have to know dA, whatever its area was. In this case, we can say that we know the height of this, T. Say we know the width of this, W. And let's say we know where that line is. We'll call that Y. So how would I get the area A? The area dA, sorry.
Once you just take your width and then, well, okay, first you would subtract your t from your y. Sorry.
The other way around?
That's right. Well, you could do that t minus the y and then multiply by width, right?
Yeah, absolutely. And that's your area dA. And we're saying it's dA. It's a differential area because it's not the area of the entire box. It's just the area of some part of the box. That's why we're calling it a dA, a differential area. Now so that gets me half of my integrand there. The other half is my y. Or rather, in this case, it's more like a y bar. It's going to be that would be a better way to state it. This distance y bar is the distance. Say again?
You broke up for a second there.
Okay.
Can you repeat that? I'm sorry.
Yeah. So instead of this being just y, it'd be better to say a y bar. It's the y that corresponds to that particular dA. And that in this case, rather in any case that we're talking about a first moment of area, it's the distance to the centroid of the differential area. So measuring up from the y-axis, there's about the center of that differential area. If I wanted to express y bar as a function of y in t, how would I do that?
Of yt.
Y like this coordinate here and this coordinate here. How would I tell you
1/2 of t?
1/2 of t?
Well, no, 1/2 of t. No, that wouldn't make sense. Would be like y plus 1/2 of t.
Okay, so 1/2 of t. That'd be like
1/2 of t.
Yeah. Half of t's not really linked to how big this thing is, how big this dA is.
1/2 of dA.
That's an area, not a length.
Killing me.
Okay. So what I want is half of this guy, right? That's what I'd really be more interested in. Half of that length.
Yeah, well, that's the.
How do I get that length?
Oh, I guess that's the W. Or no. The length. How do you get that length?
How do we get it before?
The t minus y.
You got it.
1/2 of t minus y.
1/2 of t minus y is from there to there. I hope no one's red,
Plus
green.
y.
Yeah.
Okay. I knew I was doing something with the 1/2 and the y and stuff, but I just wasn't putting them together right.
All right. So my y bar is 1/2. That's it. That's a half, I promise. T minus y plus y. Cool. And I'm sorry for people who are red-green colorblind. I'll stop using red and green together.
Looks like Christmas for the Marius. I love it.
Hey, and it's snowing outside. Life is good. So if I put all these together, I can substitute them directly into this. Which I can replace this. How do I say this? I can replace this integral because the integral y dA is called, which is my first moment of area, is equal to y bar times the dA that I've come up with. I can replace that entire integral so that it looks something like this. Assuming I can remember what I just wrote. Yeah, I'm missing something. I think it's this. If I'm writing this wrong, please let me know. I think I got it right. I can do that. Note that this is for a rectangular box beam or a rectangular cross section. Wow, it's being crappy. If you find your first moment of area for another shape, for another cross section like a circle or triangle or whatever, you'll have to recompute this. But but in the grand scheme of things, what I'm trying to say is that this integral YDA is the first moment of area, and it's something that we can find. It's something analytical, something we can just figure out. So as a result, bless you, or rather, to generalize this, I'm just going to call my first moment of area Q. All right. Cool. And I'm also going to solve for my shear force. Okay. So we're getting closer. However, we're not there yet. So let's see what we can do, because we ultimately want this guy not be a shear force but a shear stress. We want to have a shear stress expression here. We also would like these to not be two moments but one moment, or rather just something that we can compute. So let's have a go at this. Thing one, let's look at these moments here. We know that this is like a change in moment, right? Like a DM. That's just called DM would just be one moment, which is called the change in moments between two different points. So in this case, we're going between B and A. So it's just MB minus MA. That's a DM, or a difference in moment. We know that DM dx is like a shear force, right? That's what's called. We defined that back when we were looking at shear and bending moment diagrams. So therefore, if MB minus MA is a difference in moment, or a DM, that DM is equal to a shear force times dx, right? I just multiplied dm dx equals v by dx. That's all I did. So I can rewrite this guy as v dx over I times q equal to plus u dh. All right. part the first. Next step is I know stress is force over area. So if I want to get a stress on my left hand side, I have to divide by area at some point here. So I'm going to multiply by an area. Here's my, sorry, 1 over an area. So that'll give me a shear stress on this left-hand side. And conveniently, it cancels out that dx on the right hand side, leaving my shear stress expression as VQ over IT. So my shear force on a given section multiplied by my first moment of area divided by the section's second moment of area. So that is same as in bending stress. The second moment of area for the entire cross section. This is the thickness of the cross section. So, oops. Sorry. Thickness with 2 S's, I promise. So that's like how deep it is going into the board. V is your shear force straight off of your shear and bending moment diagrams. And Q says your first moment of area, which is computed as we just did before. We got any questions on where we are now?
No, I think.
Cool. All right. So now if I take that expression that I had before for Q, I'm going to substitute that guy in quick, and let's see what it looks like. Excuse me. I'm just going to finish erasing on the bottom here. Folks are okay with that. Okay, so if I take that expression that I had before for first moment of area, I plug that in here, my view for IT gig. If I take it and I simplify it, it would look something like this. I just have to make sure I get my terms correct. T is height, Y is still the same. Okay, cool. T is height, Y is still the same. Is height, Y is still the same.
Brother Marius, where are you? Random question.
Where am I personally?
Yeah. Like, where are you doing these videos from?
Oh, this is what you call. This is from our house on campus. I'm right below the science center.
Yeah.
We all
okay.
live, yeah, we
So
all,
you
yeah,
have an
we
office
all,
in that house.
we all live there.
So you have your own office in there?
No, I'm stealing an office that's in here. No, really, I am. Like, this is supposed to be the house econom's office. So the guy's in charge of all the money that has to go through the house. but he's not really using it too much right now. So I just kind of appropriated it.
Oh, that's nice.
Yeah.
Brother Marty stepped in and told him he's the big boss now.
Yeah.
I'm sorry. I realized I used the variable t twice for two different things. I'm going to change that to w. Sorry. So this is like if I have my beam, here like that. I said that was t. W is that. Okay. There's the y in there. Are we all clear on that? I'm sorry for the confusion there.
Wait, so Brother Mars, can you scroll up a little bit then?
Keep going.
Yeah, keep going.
Okay, let me change
So would
this
you
to
change that T right there? Oh, okay. I was just gonna say, would you change? Okay.
yeah.
So is that all the T's you would change?
Yeah, because all those are consistent. Yeah, all those are consistent.
Even in the Q?
Yeah,
the Q
because that T is actually half the height of the beam, whereas the T down here, this guy, that was referring to the width of the beam instead.
Oh, okay.
Yeah. Sorry, I changed. Hold. My notes had it one way, and I went off my notes for a minute. So when I come back to them now I'm all screwed. Now I'm all screwed up. So anyhow, W is the width of the beam. So like, if I have my trusty I-beam, that's like my W, and that's like my T. All right. T W.
Gotcha.
All right. So if I take my expression for Q from before, I'm just going to substitute that in, and I'm going to simplify it a bit. Comes out as something like 1/2 WT squared minus Y squared if you do the factorization. So again, this is for a rectangular cross section. But something that we can immediately tell is, okay, if I go to the top of my beam, that gives me a y coordinate of what? If we scroll back up there, the top of this beam is how far from the neutral axis?
T.
T, right. And the bottom is also T away from the neutral axis. So if I go back over here, and if I substitute T in for Y, I get 0 for this whole thing. So this means that the top and bottom of the beam, shear stress is 0. And that it's if you look at my section here, and I kind of plot shear stress on it. So the larger my lines are, the higher the shear stress is. It's going to start at 0, and because my y is squared, it's going to increase parabolically to a maximum where y equals 0, and then decrease again until it equals 0 at the opposite edge. This is our shear stress distribution. It's a parabolic distribution that depends on the geometry of the section. So I is constant. for whatever the section is. W is whatever the local width is at Y. But regardless of all this, our shear stress due to these bending loads is going to come to a maximum at the middle of the beam, which, if we remember back to the picture that was up when we started class, actually makes some sense. So if I pop back over to the presentation here and jump back to slide 1, you see where those cracks are running? They're running along where the shear stress is maximized. This beam actually failed due to shear stress first. And that's what we're going to look at next. So, next class at any rate. Are there any questions on this stuff though?
Wow. Interesting, Brother Morris, is all I have to say.
Good. Glad to hear it.
Well, it's complex.
Right.
It's pretty complex, in my opinion.
All right. Well, it's good. It's good for stretching your mind then. So that's all I got for today, guys. Thanks for stopping by. I'll see
Thank
you.
you, Brother Morris.
Okay.
Thank you.
And you said, you said the homework is due on Monday, correct?
Yeah, it's always due a week after it's assigned. So
Okay.
assigned on Monday.
Thank you.
Okay.
All right. Sounds good. Have a good one.
Y'all too. Wish you guys could see the snow. Well, you might be able to see the snow, but it's yeah, you can't really see it outside of the window.
Have
See
a
you
good
guys.
one, Brother Morris. Thank you.